We know that an infinite GP gives a finite sum if the common ratio R is less than 1 as shown. This concept has many applications and has helped to answer many puzzling questions. For example, finding the areas and perimeters of fractals. For example, the area of cock snowflake can be computed using the concept of infinite GP. It is also used in finding the perimeter of a fractal, as was done to estimate the length of the coastline of Britain. Benoit Mandelbrot was the mathematician who proved that the length of the British coastline is infinite. However, by using the concept of sum of infinite GP, later mathematicians proved that the coastline of Britain is finite. This concept is also used in dividing a finite area into infinite parts, as Archimedes did to prove the theorem that states that the total area under a parabola is 4/3 of the area of the triangle inscribed. Archimedes used his profound knowledge of mathematics and determined that each green triangle has 1/8 the area of the blue triangle, each yellow triangle has 1/8 the area of a green triangle, and so forth. Now, if the area of blue triangle is assumed to be 1, the areas of the different colored triangles form a GP with the common ratio 2 times 1/8 as shown. Hence, the total area under the parabola is an infinite sum of an obtained GP as shown. Last but not least, infinite geometric progression also finds an application in simplifying recurring decimals and expressing them as fractions. Let's explore some more applications. Express 1 by 10 plus 1 by 100 plus 1 by 1000 plus etc. as a recurring decimal. The key idea to solve the problem is to first prove that the common ratio of the consecutive terms of the given series is constant. As a result, we get the given series in geometric progression. Then use the formula to compute the sum to infinite terms of geometric progression. Since the common ratio is constant for its consecutive terms, the given series is a GP with its first term equal to 1 by 10 and its common ratio equal to 1 by 10. Since the common ratio lies between -1 and 1, by using the sum to infinity of a GP formula, we get the solution as 1 by 9. Ratio of a GP is -4 by 5 and its sum to infinity is 80 by 9. Find the first term. The key to solve the problem is to use the sum to infinity of the geometric progression and then substitute the value of R to find the first term. Consider the sum to infinity of a GP formula. Use the sum to infinity of a GP formula and equate it to 80 by 9. Call this equation 1. Substitute the value of R in equation 1 and get equation 2. Multiply both sides of equation 2 by 9 and on simplification we get the first term of the GP as 16. Jack is using a device to extract air from a bottle. The pump he uses can extract a maximum of 46 centimeters cubed of air. In practice, what happens is that the first attempt extracts 46 centimeters cubed and subsequent extractions follow a geometric sequence. Jack's second attempt extracts 36 centimeters cubed. What is the maximum amount of air he can remove in total? The key to solve the word problem is to first understand and translate it to form a geometric progression. Since the total number of attempts to extract air is not known, consider it to be infinite. Therefore, the maximum amount of air extracted will be the sum of infinite terms in geometric progression. The subsequent extractions of air from a bottle form a GP. Therefore, the amount extracted in the first attempt will be the first term in the GP. Hence, the first term is 46. As a result, the GP is obtained as shown with a common ratio R. We are given that at the second attempt, 36 centimeters cubed of air is extracted from the bottle. This implies that the second term, 46R in the GP given by 1, is 36. Now simplify equation 2 to get the values of the common ratio R as shown. Since the total number of attempts to extract air is not known, consider it to be infinite. Therefore, the maximum amount of air extracted will be the sum of infinite terms in the GP as shown. Now, substitute the values of A and R in the formula given by equation 4 and simplify as shown. Hence, the maximum amount of air extracted from a bottle is approximately 212 centimeters cubed.